So I'm going to present the work done on the topic Integrated Quality Assurance and Control Framework for BIM models during design, construction, and operation. And it was done by the supervision of José Carlos Lino, Bruno Caires in front of the BIM's company, and Elder Souza. Now, when it comes to the implementation of BIM, as we all know, it fundamentally transformed the business model of how the projects are created, developed, and collaborated. Basically by centralizing all important information within the BIM model. And this brought into the highlight quality of the models and actually increased demand for the quality assurance and quality control processes. Now, when it comes to current state on the market, there are more than a few softwares that actually address certain aspects of BIM models quality, but they're rather fragmented, which actually emphasizes the need for creating a solution that would integrate both quality assurance and quality control. Now, to actually delve into the topic of quality assurance and quality control in BIM, it is important to understand what is quality. And the most universal definition would be that quality means conformance to the requirements. Now, the need for quality actually inaugurated the discipline called quality management. Now, the common misconception is that quality management started with the Industrial Revolution. The truth is it actually evolved along with the changes of products and services, which actually leads us to this point, and that is the main question, how to address quality in the digital environment. Now, when it comes to quality assurance and quality control in BIM, they're often mistaken for the same. However, they represent two concurrent processes where QA is actually providing confidence that the quality requirements will be fulfilled, whereas quality control is basically using different verification methods and focused on fulfilling those requirements. Now, to address what is the current QA/QC status in the BIM market, a research study was conducted, basically by evaluating several guides and manuals, and here we can see the results. And actually the results of this study showed us that all of them address quality to a certain aspect, but they lack those detailed and precise guidelines, which also confirms the need for creating thorough requirements for assuring quality of the model. Now, one very important aspect are information requirements and actually level of information. And for a long time, we had the use of level of detail and level of development. And it caused a lot of misunderstandings. And even now, for each of us, LD 300 for the BIM would be different. And this actually, to overcome those limitations, level of information of need was introduced. And level of information need is based on the prerequisites, as we can see in this illustration. So it is important to answer, what is the BIM model use? So why the information is needed? What is the project milestone? So when the information is needed? Who is the actor? And what is the object? Now, when it comes to methods for specifying information requirements, as we can see here, we have more than a few, and they go from the simplest, which is text file, to something that is now gaining popularity, which is information delivery specification, otherwise known as IDS. Now, to address important aspect of BIM model quality are BIM model checking tools, and also research study was conducted to evaluate what kind of checkings do they address, what are their functionalities, how they address the rule creation process, how they visualize results. For this study, 4 tools were selected: Revit Model Checking, Solabri, Navisworks, and US BIM Checker. And the results we can see in the table. And basically proposed methodology integrates quality assurance and quality control. So quality assurance through creation of requirement specificator and quality control through that model verification process. So the proposal is to have something that is a base called requirement specificator, from which the appointing party creates a subset of project-specific requirements. Those requirements are then handed to the appointed party, which creates model based on them. sequentially exports the IFC file, then returns that IFC file to the appointing party, which then verifies compliance of the IFC file to the requirements. And the important aspect that was also addressed during the creation was the possibility of machine-to-machine interaction. So as we will see later, requirements specificator is much higher level of complexity compared to something that is conventionally used. The format, it encompasses large number of parameters, and they are sorted in a tabular format, which would actually allow advanced technologies, advanced tools to process that information. Now, this was tested on a case study in collaboration. Now, when it comes to requirement specificator, it was a result of an extensive research. So a lot of interviews conducted with the company, a lot of tools evaluated, as well as guidelines. The specificator follows a class hierarchy inheritance, meaning that lower tiers inherit functionalities from the upper ones. As we can see, it consists of 3 tiers. So it goes from more general, which addresses fundamental requirements important for effective collaboration, so georeferencing, consistency of units, and so on. Then we go to the second tier, and it is more detailed, so it addresses modeling requirements, alphanumerical, geometrical, design specific, and model content, architectural, structural, MEP. And we have finer division according to project stages. In this case, it was decided to have 3, so design, construction, and operation. And third tier, which is also, it is actually structured the same as the second, so it addresses requirements and content, but it is focused on specific BIM uses, in this case, cost estimation and energy analysis. Now here we can see modeling requirements, they all follow the same rule schema. So shall is expressing a requirement that must be followed, should and may something that is a recommendation, and can something that is a possibility. As we can see in this example, they can be used in a combination to address one requirement. So here in BIM file naming, we know that all files must follow uniform and consistent naming convention. And then we have an ISO naming standard that the client can choose to follow. And majority of requirements consists of these guidelines that are either proposed by ISO standards or by company professionals and their experience. Now, when it comes to model content, it is addressed through level of information need. As already mentioned, it is in tabular configuration. And each parameter consists of description, data type, and corresponding unit. Now, in this example of the wall, we can see that quantity of information with each phase grows exponentially. And it is important to know that not only the number of parameters change, but it also become more specific. So if we in design phase have something that is estimated reinforcement, in construction and on operation, it will become an actual calculated value. And now here we have a quantitative overview of created requirements. Here we can see the requirements and their accompanying guidelines, as well as the elements and accompanying number of parameters. But overall, 75 modeling requirements, 182 level of information need, and overall, at this stage, 4,693 rules that can actually be employed in the verification process. Now here we can see the first verification method that was tested, Dynamo, and basically 3 checkings were performed using Dynamo. Here we can see that apart from standard nodes, also Python scripts were employed where it proved to be more efficient. And in the displaying of the results, we can see that in the first unique room naming, they're actually displayed in Revit environment. whereas in the second, which actually checks for unplaced rooms, it is exported as an Excel spreadsheet. And we have third verification, actually third checking. That was the most complex since it combines the architectural model and the MEP model that is linked. So it uses a package that is specially made for working with linked elements. And this checking actually displays results both in Excel with relevant data and in all Revit views. An actually important aspect with working with Dynamo for performing these checkings are how to display the results so the users can actually use and process that information. Now, the second verification method was using Python and IFC OpenShell. Again, 3 checkings, and they were all based on if conditions, meaning they provide pass or fail results. Now, the first one was checking if for the minimum handrail height, and it is the most straightforward because it accesses the height that is stored in the property set of these IFC railing objects. The second one is more complex because it employs geometrical calculations. So it does not access the property value, the parameter value directly, but it actually employs vertices and faces to create the areas and compare them to the room schedules given by the client. And we have the third one, which is actually based on elements relationship. So it follows the IFC schema. So basically, first, all wall elements are retrieved. Then following the IFC schema, so going through IFC rail voids, opening elements, filling elements, we find the walls and doors that are hosted. Then we compare their location and we see if there is a mismatch. And third verification method that was using IDS, and actually 2 approaches were tested. One that is completely open, using IDS converter and IFC tester within Blender BIM. And second one, which is editor and validator from Mecha software. Overall, they follow the same principles with the difference where IDS converter actually consists of firstly populating Excel template, then using the converter to convert it to IDS, and then compare the IFC file to that IDS. And what is important, the IDS converter shows limitations. So it only addresses properties. Or actually, it can be used only to specify properties and their values. So no attributes, no classifications, no materials. Basically, no values that are stored in higher entities within IFC schema. Whereas editor allows us all of that with certain limitations when it comes to the materials. And here in the visualization of results, we can actually see that both of these approaches showed identical results with 33 wall instances missing certain dimensional data. Now, when it comes to conclusions of this work, the proposed methodology holds great potential for integrating QA and QC. Though the reality is that its full implementation would require an extensive amount of resources, both financial and human, and Specificator would require constant refinement, aligning it to the current industry standards. Some of the further development proposals are to enlarge the Specificator by adding more project-specific parameters, more BIM uses, then to enhance verification methodology and actually to incorporate all of the rules, all of the requirements, then to centralize all of them in one web-based platform, and most importantly, to actually facilitate that machine-to-machine interaction. And to address that, creation of preparator is suggested. So basically, we would have a preparator where the client would enter only a few input data, such as what is the building type, what is the project milestone, what are the BIM uses. Then automatic generation of those project-specific requirements would happen from the repository and based on those several inputs. And then also automatic verification of the IFC file to those requirements. But overall, this research underlines the importance of the industry to prioritize BIM model quality and actually to adopt methodologies that are straightforward, that are integrated, and that are applicable in the real world market. And thank you for your attention.